Gravitational waves ripple through spacetime, carrying information across billions of light years without losing strength. This could redefine how we communicate beyond our solar system. Unlike radio waves, gravitational waves aren't scattered or distorted by atmospheres or solar storms, making them ideal for reliable signals in harsh cosmic environments. Signals carried by gravitational waves maintain consistent quality over immense distances, unlike electromagnetic waves that weaken and distort, limiting current space communication range. Electromagnetic communication faces challenges like signal diffusion, reflection, and interference from solar activity, which gravitational waves can overcome due to their unique nature. Creating artificial gravitational waves strong enough for communication remains a massive technical hurdle, requiring enormous masses moving at incredible speeds in laboratory conditions. Colliding massive objects like black holes produce gravitational waves that ripple through space-time, carrying energy and information across billions of light years without losing strength. These waves travel unimpeded by matter or electromagnetic interference, unlike radio signals that weaken or scatter, making gravitational waves ideal for communication over cosmic distances. Generating detectable gravitational waves artificially remains a massive challenge, requiring technology capable of manipulating enormous masses or energies in controlled environments. Physicist Kip Thorney's work on gravitational waves earned a Nobel Prize in 2017, confirming their existence and inspiring new research into their potential for communication. The LIGO Observatory in Hanford, Washington, was the first to detect gravitational waves in 2015, marking a historic breakthrough in astrophysics and opening new communication possibilities. The challenge of producing artificial gravitational waves lies in moving enormous masses at incredible speeds, something current technology cannot achieve outside cosmic events. The Virgo interferometer in Italy, alongside LIGO, forms a global network detecting gravitational waves, improving localization of cosmic events since 2017. Nobel laureate Rainer Weiss co-founded LIGO, forms a global network detecting gravitational waves, improving localization of cosmic events since 2017. Nobel laureate Rainer Weiss co-founded LIGO, pioneering laser interferometry techniques that measure distortions smaller than a proton's diameter caused by passing gravitational waves. Advanced quantum sensors and ultra-stable lasers are being developed to enhance gravitational wave detection sensitivity, pushing boundaries of precision measurement in physics. The European Space Agency's ESA mission, obscene, planned for the 2030s, will deploy three spacecraft millions of kilometers apart to detect low-frequency gravitational waves from massive black hole mergers. Hao Tianfu Wang and Osgur B. Akan from Cambridge University recently proposed a theoretical framework for gravitational wave communication, outlining potential protocols for encoding data. Testing these ideas requires simulating gravitational waves in controlled environments, pushing experimental physics to its limits with ultra-precise vibration and resonance setups. The Max Planck Institute for Gravitational Physics in Germany leads many experimental efforts, combining quantum optics and mechanical engineering to detect faint gravitational signals. In 2024, the GEO 600 detector in Germany demonstrated enhanced sensitivity using squeezed light, a quantum technique that reduces noise in gravitational wave measurements. Future space-based detectors may combine these advances, enabling gravitational wave communication networks that could span the entire solar system and beyond. Physicist Rainer Weiss, a co-founder of LIGO, also contributed to gravitational wave communication concepts, linking fundamental physics to potential future technologies. The California Institute of Technology, home to LIGO's headquarters, continues pushing boundaries in gravitational wave detection and communication research. Simulating gravitational waves in laboratory conditions demands ultra-sensitive equipment and vibration isolation, similar to tuning a violin in a noisy concert hall. Nobel laureate Kip Thorne's theoretical work laid groundwork for understanding gravitational waves properties, crucial for envisioning their use in communication systems. The Laser Interferometer Space Antenna mission, led by ESA, aims to detect low-frequency gravitational waves from space. The California Institute of Technology, home to LIGO's headquarters, continues pushing boundaries in gravitational wave detection and communication research. Simulating gravitational waves in laboratory conditions demands ultra-sensitive equipment and vibration isolation, similar to tuning a violin in a noisy concert hall. Nobel laureate Kip Thorne's theoretical work laid groundwork for understanding gravitational waves properties, crucial for envisioning their use in communication systems. The Laser Interferometer Space Antenna mission, led by ESA, aims to detect low-frequency gravitational waves from space, a key step toward practical gravitational communication. Harnessing naturally occurring gravitational waves could slash the energy needed for communication, but capturing and modulating them requires breakthroughs in detection and control technology. The Max Planck Institute for Gravitational Physics in Germany leads efforts to refine gravitational wave detectors, pushing sensitivity limits to unlock new communication possibilities. In 2025, the Laser Interferometer Space Antenna, or LISA, launched by the European Space Agency, began testing space-based gravitational wave detection beyond Earth's atmosphere. Quantum sensors integrated with ultra-stable lasers now approach the precision needed to manipulate gravitational waves, similar to tuning a radio but on a cosmic scale. Rainer Weiss, a pioneer in laser interferometry, continues to influence gravitational wave research that could one day enable communication across light years without signal loss. In 2019, the GEO 600 detector in Germany unexpectedly observed subtle noise patterns possibly linked to quantum fluctuations, hinting at new gravitational wave detection methods. These quantum fluctuations act like ripples on a pond's surface, tiny disturbances that could amplify gravitational signals, turning faint whispers into detectable messages. The European Space Agency's ELISA Pathfinder mission, launched in 2015, successfully tested technologies crucial for future space-based gravitational wave observatories. ELISA Pathfinder's precision control resembles a tightrope walker balancing on a wire thinner than a human hair, maintaining stability in the vacuum of space. Looking ahead, merging gravitational wave communication with quantum encryption could create unhackable channels, transforming how humanity exchanges information across the cosmos. Harnessing naturally occurring gravitational waves could drastically reduce the energy needed for communication, opening possibilities for deep space missions beyond our current reach. The key challenge remains generating artificial gravitational waves strong enough to encode meaningful data, as current technology cannot produce waves detectable beyond cosmic noise. One approach involves manipulating ultra-dense materials or rapidly spinning massive objects to create tiny ripples in spacetime, similar to how a boat creates waves in water. If successful, gravitational wave communication could bypass interference from solar storms and cosmic dust, enabling reliable data transmission across billions of kilometers. This technology challenges us to rethink communication fundamentals, hinting at a future where messages traverse the universe unimpeded, reshaping interstellar exploration forever. The part nobody talks about is energy efficiency. Harnessing naturally occurring gravitational waves could reduce power needs drastically, making interstellar communication more sustainable and feasible. If this changed how you think about this topic, hit subscribe. We break down one mind bending concept every week. Links to sources are in the description.